Okay, last time we have learned, or we have introduced to I've introduced you to double integrals in polar coordinate. So as you can see from the polar, that what you are going to integrate is, of course, the polar equations, the r and theta, the functions of r and theta. And when you look at the form, if you define as sums of this 2 sigma here, and you define the functions for let's say the surface, and then define the other one as the area, and you have now the area in terms of polar, which you can define as r, delta r, and delta theta. You can see from the this illustration here, if you want to cut into pieces this polar plane, you will get this small rectangle here, in which those rectangle are, we can simplify and approach a difference in the large sector and then the minus the small sector. And that is why we have the Ri here and delta R, okay? And we are going to use these 3 variables here, Ri, delta R, and delta theta, to be our integration here. Okay, so every polar, if you want to, let's say, convert from just xy, and you want to convert to r cos theta and r sine theta, okay, whenever you are in the double integral, your dx dy or your dy dx, okay, this is f, let's say just f, this should be changed. Okay, this dA should be changed into r dr d theta, and still a function here. Okay, that's the important point that I want to emphasize. Let me give you the okay. Okay, I think I can give you some example. I think we can start by first example for a polar. If you have this okay, let's evaluate. So evaluate this double integral. Of course, if you look at the integral, there's nothing wrong with the integrations. We can do the inside integrations, the first step here, integrating this. And then you can have integrating with respect to y. And then you can have x squared plus, it's become y cubed, right? 3. And then you need to plug in the 0 to square root of 1 minus x squared, and then still have the other integrations, the dx, okay? And then you need to plug in this to here, and then it starts to be a complicated solutions, right? So you will have the, and you need to solve this, and then later to be integrated. Of course, you can do this as well to check what is the solutions. But instead of doing all this, let's see from the form itself. Okay. So the idea is we can look first dx. It starts with the constant -1 to +1. Okay. And look at y. Okay, dy. It starts from y equals 0 and ends up with y equal square root of 1 minus x squared. Okay. Now first, look at y equal 1 minus x squared. If we try to simplify this, we can have these terms, right? Okay. And we know that this is a circle, right? So basically, we can try to check what is the shape of at least we check the boundary of all the integrations. So we can check the plane xy. Okay, so we check xy. So it starts from -1 to 1 for x, right? So let's say this is x, this is y. Okay, and then we start from, let's say this is -1 and this is 1. Okay. And then for y, it starts from 0 to this, right? If you check and try to plug in the point, you will get that, of course, it will be this is 1, and it will be a semicircle, right? Because it starts from 0. It can be a full circle if it is start from negative square root of 1 minus x squared. It will be a full circle. But since it starts from 0, then we can conclude that it is on only on y positive, right? So from 0 to y positive. So this is our area. Since we know that this is a circle or semicircle, then we can actually, or maybe we can write step by step if you want. We can also write this. Since this xy is from -1 to 1, and y is from 0 to square root of 1 minus x squared. Since this is the r, we can convert, right, x and y to polar. If you look here, okay, if you look this semicircle, we agree that the radius is 1, right? The radius is 1. And also, if you look at only the semicircle, we agree also that the theta is from 0 to pi. Okay? And then we can also write the r is also, if you want to convert to r theta, then you will have 0 to pi, okay, and then 0 to 1, okay. And then we have, let me write the original equation. This is dy dx, and then it's equal. And remember, the thing about the polar, it's always, if you want to change dy dx or dx dy, it's always changed to r, dr, and the theta. So the theta is always on the outside integrations, and r is inside. And what is the functions? The functions is x squared plus, here, x squared plus y squared, which is r squared. So we need to multiply with r squared. Okay, here is our functions now. And we can have, this is r cubed, right? R cubed dr. Actually, if you can separate the variables, you can actually write like this. And you can integrate this, become pi, and this will become r with power of 4 equal 4. And then you can multiply, become pi over 4. Okay. I hope you get it, the idea on how we can actually convert any integrations that you are pretty sure that this integral, this double integral, is having relations with a circle, okay, or a polar equations, okay. And you can convert x, y to the r and theta, and it will be helpful, right? Instead of solving this, right? Instead of solving this solutions through regular integrations, you can convert and make a simple solution as this example. Okay, I hope you get all the points here. Let me give you another example. Okay, let's say we have double integral, and then this functions is sine theta and dA. And the questions R is a region outside circle R equal 2, and inside a polar equation 2 plus 2 cosine theta in first quadrant. So that's the R. So evaluate the double integral. Okay, do you want to try? So yeah, you can try. So the question is just sine theta, the double integral, and then the first thing that you need to make, or you need to do, is basically define R. Define R in terms of which area that the R is going to have. And as we have learned also in previous courses, the integrations, how to take the boundary. That's important. So you have this R, right? But you need to define which are the top boundary, which are the lower boundary. Okay. So it's important to at least draw the rough sketch of the graph. So basically, you need to draw first the circle, and then draw this the other polar. This time is the cardioid, right? The cardioid. Okay, you can also try if you want. Try by yourself. Okay, let's say this is our polar from 0 to pi over 2. And then let's say we have, oh, wait. Let's say this is our circle. And then to draw the cardioid, we need to look for, it has 2 and 2. So the maximum, the longest length it has is 4, right? So probably 4 is here. And because it's cardioid, it should be intersect at this 2. Okay. So at least that is our our sketch. Okay. And then outside of circle, inside the cardioid, but only on first quadrant. First quadrant means only at here. This when all sine or cosine are positive, right? So this is r2 plus 2 cos theta, and this second one is r equal to 2. Now we already have all the informations we need, right? So we have the theta from 0 to pi over 2, and also from r, this 2r. Okay, so we can use all these informations as our r. So we can check or write down on the double integral 2 plus 2 cos theta. And this is sine theta r dr d theta. Okay, we can actually write down that the r, when you integrate, it will be r squared, right? And then you still have sine theta, and then you need to plug in this value, and you still have the integrations. Right? So let's start to plug in the integrations. So you still have this value, and then you have half sine theta, and then we plug in here, so 2 plus 2 cos theta, and then squared, and then minus 4, okay, and then d theta. Okay, we need to have at least, you need to use some method from calculus 1 to solve this for integrations method. Okay, so we first solve this sine theta over 2. This will be 4 plus 8 cos theta plus 4 cos squared theta. So I will directly write this 8 cos theta plus 4 cos squared theta and d theta. And then solve this, make it 4 and 2. And let me factorize 2. And then it will be, and then multiply with sine. So 2 sine theta cos theta plus sine theta cos squared theta. Okay. And then d theta. Okay, this part, the first sine theta cos theta, you can write this as sine 2 theta, right? And you can integrate this easily, right? It will be negative cos 2 theta over 2, right? And the other part here, so you can actually integrate separately and then combine at the end. So you can use the use substitutions method, if you remember. Let this cos as the u, and then we differentiate, and we get the relations between u and theta. And the idea is to make or to cancel this sign, right? And you have the u squared, it become u cubed over 3, right? And you cube over 3 is basically 1/3 of cos, and then cube theta. And then you can plug in the value. This is also, you can plug in the value, and then you can plus this, right? Plus this, and you get the solutions. Okay, I will leave the solutions to you. You can solve this until finish. I think should be 8/3. If I'm not mistaken, I also haven't finished this, but I will skip the final product, okay, and go to another example for you. Okay, so this is example for the polar. So because we are discussing about polar, so everything related to polar equations, the circle, the cardioid, the Rose's curve, the lemniscate, all of that types probably will be in our equations. Okay. Okay, I will give you one more cases, or maybe two more, but I think one more, and then we can move on. Okay, another example. Find volume of solid bounded by z equals 0 and z equal 1 minus x squared minus y squared. Okay. Now, what is actually this questions? So you need to define first. Okay. What is the shape of or the volume, or can you make it into? Because you see the giveaway is this x squared and this y squared, that you can think about circular, right? About anything related to circle, right? At least x squared and y squared. If you look at or imagine z is 0, then you can have x squared plus y squared is 1. So at the very base, we have a circle. And of course, if you remember, if you look at the z and x squared, and then also z and y squared, both are having parabola, right? Parabola relation. So this is the surface of paraboloid. And the type is a circular paraboloid, because you have a circle as its base, right? Circular paraboloid. So if you want to draw, you can draw, but I think if you already have an idea to solve, you can directly write your solutions. But if you're still confused, you can draw and then imagine, at least draw what it looks like for the area at the base of xy. So we have this circle, x squared plus y squared equal 1. So we have a circle here. Let's draw a circle. So let's say this is x squared plus y squared equal 1. Okay, the circle. And where is the parabola? Well, parabola will be probably here, maybe 2, maybe like that. Okay, that's the parabola. I hope you can see the paraboloid. Okay. Now, if we look at the circle here, we can trace the circle, or we can use in terms of, oh sorry, y or x equal, okay, y equal 1 minus y squared, or y equal 1 minus x squared. Okay. Okay, then we can try to evaluate. Okay, the volume will be, so the volume will be, so from 0 to z equal this paraboloid. So the paraboloid itself is our functions. So let's write here. So let's write the xy, the rectangular coordinates. So first, maybe start from, I want to start from dy there, but you can write the x dy. That's the same. And start from, because it's equal -1 to 1 for the radius, right? See here, this is the x, right, equal 1, and this is -1. So this is x. Okay. And then for the y, we will have, because it's a full circle, we will have negative and positive. Okay. And of course, if you want to try and solve this in terms of x and y, you will get complicated solutions, because you have this square root, right? These two square root. Then the idea is, okay, let's convert to polar. So volume is from 0 to pi. Actually, if you can see from the beginning that you can convert to polar, you can skip all this xy process and directly go to the polar. Okay. So this 1 minus x squared minus y squared, you can simply just say, oh, this is 1 minus r squared, right? So you can use that. So this is the theta, and the radius is from 0 to 1, because there is no other radius besides 1, right? So we can write 1 minus r squared, and then r dr d theta. Okay, remember, this is important. Usually when you are in the exam or solving problems, you need, or you are usually tend to be missing this r. Okay, no, I've warned you. Okay, from what I've given since previous lectures from the last year student, or 2 years 2 years back, the students always missing this r. Okay, and that's why they have mistakenly have wrong solutions. Okay, now we have volume, and then we can separate theta and r. So we can do this, right? And then we can evaluate the r. And then simply we have this is 2 pi. And then we have r minus r4, and then from 0 to 1. So we have 2 pi. Oh, sorry. This should be r. This should be r squared over 2. Half minus, or we can This is 1/4. 1/4, it's pi/2. Okay. Okay, I think okay, I think we can just move on. Okay, I think we can move on to another sections. Okay, so this will end our 15.3 ends here. Okay. Okay, any questions first? Any questions first? So every time you have dy dx and you want or dx dy, sometimes it will be easier if you just use polar. If you can relate the equations into a polar, okay? Unless it's not a polar, okay? Okay, now the next part is actually 15.4. But since if I look at the chapter or the sections, it's mostly about physics. So I will skip skip 15.4. Okay, so you don't need to check or observe 15.4. So we are going to have now is 15.5. Okay, 15.5 is the surface area. Okay. Let me check if do I have it now? Oh, I think I haven't. Okay. Let's start to building the what's the foundation of the surface area here. Let's say we have the surface. Let's just say that this is a random surface. Okay, and then we can map on this surface here. And observe at a point here. Okay, so this is, let's say this is our Pij to make it more specific at that point. And then from this P, we can draw its tangent plane. Okay, its tangent plane. Let me draw here and here. Okay, that's the tangent plane. Okay, so you have now you can see the gap here, right, between the plane and the surface. Okay, imagine there is a gap there. Okay, the next thing is and let's say because it's very small, let's name this plane as the delta phi. And then let's map all this surface into xy plane. Okay, maybe using different color. Okay, let's say that's our map. Mapping from the surface into the XY plane. And let's say this is the delta of x, and this will be the delta y. Okay. Okay. And let's name this region is R. And we have in this R is our delta A. Okay. Okay, now to make it more, let me move this first. Okay. Let me write some notes here. The tangent plane of the surface to point P is approximation to S near this point, right? And we can say the delta T, it's part of tangent plane, right? It's cut into pieces, right? The tangent plane. And the tangent plane itself, we can say that the tangent plane is a parallelogram. So that lies directly above the R. Is an approximation to total area of S. Okay, that's the definition of the delta T. So we define the surface area. So the surface area or surface area A is limit Sm and approaching infinity of the delta T. Okay. Now, to observe this delta T, let's try let's observe this tangent plane into more clear visual. So let me move to the next slide. If you have any questions, or maybe you need to maybe to slow down my drawing, you can chat in the chat box. Okay. Okay. Okay, I think wait. I think it's better if this Y is here. So I can manage the consistency of the drawing. Okay, let's say this is the R. Okay. This is the R. Okay. And this is the tangent plane. Let me use the red color. Okay, maybe that. Okay. Okay, this is the tangent plane. Okay. So this is the delta T. Okay. And now let's define from this point here, from P, we will define a factor. So first is a factor A and B. Okay, let factor A, factor B is a factors that start from B and lie along the sides of delta t. Okay. And if you remember, area of parallelogram, the delta t, right, is actually the area is, if A and B is the vector at the sites, it's actually A cross B, and then you calculate the magnitude, the length. Okay. And also, if you remember, the partial x and partial y, both are slopes, right? Slopes of the tangent line through B in the direction vector A and vector B. So therefore, vector A we can define as delta x I. So here, this delta x, okay, and this will be delta y over here. Okay, so delta x I plus the slopes, okay, plus the slopes from the tangent, right? And multiply with the delta x and then k. And then delta j show y to let you know there is a component of this plane, right? Okay. Okay, so first we can calculate A cross x 0 and then partial x. Now let me write just partial x and delta x. Okay, and then later I will put in the point. This is 0, delta y, partial y. Okay, we can solve this and write as negative partial x plus partial y and j and plus delta x delta y, or the y-x is the same. All these terms we can write as delta A. Okay, and now we can factorize the partial. Oh, Okay, let me check. I think it's delay. Oh, yeah. Okay. Why? Okay, give me a few minutes. Okay, give me a few minutes to solve this. Okay, is there any delay? Okay, is there any delay? Okay, wait a minute. Yeah, wait. Wait a minute. Okay. Okay. Okay, is it clear now? Is there any delay? I think clear, right? Okay. Okay. Yeah, sorry. Why every Thursday it's always like this? I'm not sure with the connections, but I think now should be okay. Because before I'm using Wi-Fi, now I'm using the cable. Okay, we have these equations now. Okay, let's continue. So after we cross these two factors, A cross B, this is the result. Okay, and then we can rewrite the delta t from these equations, in which we can just add the square root. Okay, we can add the square root, and then we can just squaring all the informations for partial x squared, and then plus. Okay, the negative part will be gone, right? Because it's squared. Okay, and then plus 1. And then this is still the delta A. Okay. Okay. Now from the previous equations, we have limit, right? I will directly write the equations, or let me write the sigma m n and then let me write delta t, and let's replace delta t with the whole function here, or let me just write this square root of this. Okay, let me write this as and then plus 1. And then this is the delta A. And based on our definitions of limit, the surface area becomes double integral of some area R, or maybe D, if you want to define this. And then write down the square root. So practically the square root is from the measure of the length. Okay. Oh, still delay. Yeah. Wait a minute. Okay. Okay. Okay, let me check. Okay, this is the equations. Okay, okay. So this is the equation for surface area. Okay. Okay. So sorry for the delay and lagging. I'm not sure what is happening. So the definitions is this. This is the area. Okay. Area of the surface. Don't you asking why the k of the vector a and b? Um, here. Let me write here. So from this a here, it has this, right? So this I and k. Got it? Got it? No? And the k is the, okay. Okay, so remember that this f is a partial derivative, right? The partial derivative is the, you can write this, right? The partial derivative is the slope, right? The slope of the, um, yeah, like this slope of the tangent line through the point P. Okay, did you get it? Okay, 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 okay. Okay, yeah. Let me just add some notes here. The area of the surface with equations z equal these functions, and the points are it in its domain where the functions, or where the partial x, sorry, and partial y both are continuous. So basically this is the definition of the surface area. Okay, so this will be the surface area with z equal functions of two variables, and you need to make sure that the partial of x and partial of y both are continuous. Okay, maybe giving you one example for the surface. Okay, maybe the example I can write here. Okay, now we have these questions. The functions is z equal x squared plus 2y. So this is the function or the surface that are above the, we have a triangle with these coordinates, okay, triangular region. The idea first is to draw the region, okay, the xy plane. So first, this is the 0, 0. Okay, let's say that's our triangle. So this is 1, 0, and this 1, 1. Okay, we can start from partial, looking for partial x. This is 2x, and looking for partial y, which is 2. And then we can just try to plug in first to do our equations. Let's say this is r, or maybe d. You can write first here. And then we have partial x is 4x squared, right? You are squaring 2x and squaring 2 become 4, and then plus 1, so plus 5. Okay? And then you can write dA. Okay, now we can look for the boundary from here. We can look for the boundary, let's say from x. So from x equal 0, this is x equals 0 until x equal 1. You can see that it is changing its y, right, through here. Okay, and we know that because it's just a line. This is y equal x, okay, because we know the point, right? 0, 0, 1, 0, and 1, 1. So it must be y equal x. So if you want to make x as a constant, 0 to 1, we could write the term here is 0 to 1. It's x, so it should be dy dx. And the second one is y. So y equals 0 to y equal x. Okay? And then 4x squared plus 5, and then dy and dx. And then we can start to integrate. So integrate with respect to y. So we will have y, and then 4x squared plus 5. Okay. And then plug in 0 to x. Okay. And then solve this. You will get x. Okay. So in order to solve this, again, you need to at least remember the substitutions, right? Or use sub method. You can substitute the 4x squared plus 5, right? And then this become 8x. And we can substitute and substitute here. Okay. So we can integrate. This become 1 over 8. Integrate. So integrate first, and then turn back u to 4x squared plus 5. And then you get the solutions. Okay. Okay. I think I will leave the solutions, the exact solutions to you. And I think we can move on to other subject. The other subject is the triple integrals. So let's say the 15.6, I will end here. Okay. I will review again, maybe next week, about the, oh, sorry, 5, about the 15 point, from 15.2, 3, and 5. Maybe we can have some exercise. So I will move a little bit faster so that we can have some exercise, okay, to prepare the final exam. Okay, let me move to the new page. Okay, new page. This is the triple integrals. So what's the idea behind the triple integrals? Let me check first. Do I have the picture? Oh, I think I have this. Okay. So if you look here, I have this building blocks, right? We call this, let's say we define this as B, okay? And B is let's define each sides. And let's say this is the sides. So AB for X, CD for Y, and RS for Z. As you may see from the building blocks here, it's basically composed of small blocks, right? And that's actually the key for the triple integrals. So let's see the small blocks in more details here. So this is, let's say we have now 3 components, okay? I, J, and K, right? And it will determine, we have delta Y, we have delta X, we have delta Z, okay? So let me add some notes, okay? So we have a closed solid B. Okay, so it contains in a box. And then the next part is we divide B into sub boxes. And then volume of each box is, let's say, delta V. And the point of box is xijk, yijk, cijk. And then from here, okay, from these boxes, it's actually small box inside a huge solids volume, right? Now we can write down that the triple Riemann sum from these conditions, okay, we can write triple means 3 sigma like that. Let's say from L, M, N. And this is the functions. And then delta V. And from here, we can take on to our definitions. So the triple integral of f over the box B is and write down all these sigma, triple sigma, L, M, N. I hope you can read my writing. Okay. So now, instead of delta A, we have delta V. Okay. Okay. That's the definition. First, the definition. Okay. Next is also, as in previous double integral, we also have the Fubini theorem. So if f is continuous on rectangular box B, and B is basically a volume, as I mentioned, this is X, this is Y, this is Z, okay? Then we can set up the integrations. let's say we have dx, dy, dz, so we can write from R, S, and then C, D, and then A, B. And then we can reverse the order. We can write in terms of dy, dx, dz. We can write dy, dz, dx. We can also write dz, dy, dx. So we can exchange all this order. Okay. Okay. Let's start with a simple example on how we can compute our triple integral. Okay. Let's say we have triple integrations with G as the region of volume. And let's define G as we have X from 0 to 1. We have Y from -1 to 2. And we have Z from 0 to 3. So basically, from what we have seen here, we can deploy any order as we want, as long as it is suitable with the G, right? So X is 0, 1, Y is -1, 2, okay? So I write triple integral, and then let me write, this is the equations. And maybe we can start with, let's start just this first. So X is the outside integral, is 0, 1, and then -1, 2 for Y, and then Z is 0, 3. And because you can see that the function itself, you can separate X, Y, and Z squared, right? We can also write here and you can solve this. Or if you want to solve the put here, if you want to solve through iterated integral from the inside here, you can also do that as well. So it will be x, y, z cubed, and then plug in this point. And you will get 9xy, right? And then you can integral with respect to y. It's become 9/2. Wait, a little bit delay. Okay, 9/2. And then plug in this second one. And then you can check until you get the final solutions. Okay. The important point here, I think, is basically on how you are going to solve the if you have the boundary is another functions. That will be quite tough challenge. Okay, let me move to the next page. So this will be the triple integrals. Wait a moment. Okay. Okay, over general regions. Okay, first, let's look at this graph. Let's say you have solids here. Let's say this is called E. Wait a moment. Okay. And the same, it's projecting through XY plane. You have another region here. Let's say it's D. And through this E, what's interesting is it has two level surface, right? So it has the two functions. Okay? It has two functions or two level surface. So let's write some notes here. So let's solid E is a solid with upper surface and lower surface. And D is the projection of E on XY plane. Now what we are going to do now is we can define E in terms of triple integration like this and dv. And we can make it equal because now we have the functions on the level surface. So we can have, let's say this is D, and take the integrations from this lower surface to the upper surface. And then dz and dA. Now for D, it can be dx dy, it can be dy dx. Okay. So first, to solve this, of course, the first one is you need to find their surface. Okay, find upper and lower surface. The boundary of E, right? And then the second, make 2D sketch for D, the projections. Okay? And then treat this D as double integral. Okay, get it? Okay, so this is what I have summarized, at least the introduction for the triple integrals of our general region. Okay, so E is our general region for solid. And if you check your textbook, it is having each explanations about the first is dx dy, and the second is the dy dx, in which actually in a real case when you are solving the problems, that's depend on the case. Each case will be different. So I think it will be very suitable for you to solve the questions based on the general equation. So I will just give you this, and then we can see more clearly in terms of what we can define from the questions. Okay, maybe I can give you some picture here. Let me check. Okay. If you see here, this is having the y here. So this will be type 1 plane region. We know that we have two types, right? We have type 1, we have type 2, right? If you remember. So from here, if you look at y is function of x, right? So it will be so you will know at least how to define the boundary. So the boundary is really important here. Let's say this is G1, right? And then G2. And this will be the X, right? X1, X2. So of course, this will be the Z, dy, and the X. I hope you get my point, okay? If you have another, let's say, function of y, then this will be y, right? And because we can have more and more variations, of course, this can be functions yz, right? And functions of xz, right? For the this part here. But remember, when you see this pattern, look on how the patterns develop. Okay, the double variables or two variables is always inside here, and this will be double integral as usual, what you did in the previous sections. Okay, and yeah, I think the most important thing for the triple integrals is setting the boundary, not solving the solutions or finding the solution, but the first one you need to take care is set up the boundary. Or boundaries. This is the key. So if you know and you can define from the equations you get or the questions you get from the examples or from the exercise, I will attach exercise later on your Google Classroom. You will notice the patterns. Okay, I think I will stop here for now. Next week I will show you the maybe a little bit review and example, and then show you how we are going to use this setup for triple integrals. Okay. So what I'm going to do is actually we are going through to finish the chapter 15, and if we have spare time, we can have more exercise. Okay, more exercise. Okay, any questions? Okay, if no, I'm sorry for, I don't know, every Thursday. I'm not sure what is happening to my internet connections, but I'm trying to check and maybe prepare more for the courses. Okay. Okay, if there's no questions, so I will stop until here, and see you again next week. Okay, I will stop the recording.